All right, it's 9 a.m. So we're going to go ahead and get started. Thank you all for joining this month's TigerStream Stormwater webinar. Our speaker this month is Dr. Blake Whitman. Blake is an assistant professor at the University of Tennessee, Knoxville, where he teaches in the Construction Science and Management program. He has extensive experience teaching principles of construction management, construction safety, and stormwater management. His research centers on improving stormwater best management practices, addressing both construction and post-construction stormwater challenges. His work aims to bridge the gap between applied research and real-world implementation, driving innovations that enhance industry practices. He'll be presenting on some sediment barrier research that he's completed. If you have any questions, we have the Q&A function, and they'll be answered at the end. Thank you.
Thanks, Brian. You hear me fine? Just to confirm.
Yep, you're good.
Excellent. All right. Welcome, everyone. Thanks for joining us today for the webinar. As Brian said, I'm an assistant professor at the University of Tennessee. Today, our discussion topic is going to be some research I did a few years ago that was looking at trying to not only evaluate geotextiles that we use in silt fence applications, but also to create a new method for evaluating them. So trying to go above and beyond what ASTM has actually got set for us. So this is a little presentation on what I did and what I came up with. So the first question here, what is a geotextile fabric? So there are there's a lot of different kinds that we can get out there. There are different weights. There are different ways that they're manufactured. What I've learned since I've left Alabama and I'm in Tennessee is that what is actually used changes all over the country. What I thought was a pretty common fabric like this nonwoven that is used a lot by like the Alabama DOT is not used at all in Tennessee by the Tennessee DOT. So when I started thinking about this, I was like, well, what are all the different sources of geotextiles that are out there? And I started thinking about what are some different common ones that we can actually evaluate. So that's kind of where this kind of started. So when we look at some ASTM standards for evaluating this, ASTM D5141, this is the standard test method for determining filtering efficiency and flow rate of the filtration component for sediment barrier devices. So this is a unique test because it does a few different things. It allows us to take a sample and be able to test it pretty effectively in a small apparatus, so the apparatus can be easily constructed. But there are some limitations to this. So when I started looking at how this test is actually run, I was like, this is not what it actually is out in the field at all. So how can we actually mimic real runoff more accurately than what this ASTM is? So to kind of give you an idea of what this test apparatus looks like, you can go to the ASTMs and actually get a drawing of it, and TRI actually has one that they built. So essentially, it's this small little apparatus, and it's about 3 feet wide, 2.8 feet wide. It's about 4 feet long, and it's on a slope of 8%. So it's not a giant test apparatus by no means. And then you install a piece of geotextile fabric across the opening here, and you can actually include an extension box to help collect all the water, but that's absolutely not required, but it helps just trying to manage what's going on. And then you have a 20-gallon tank. So this tank's filled with water, mixed with sediment, and then it's all released at one time by opening a valve and letting it drain down to the silt fence. And that's, in a nutshell, how this test is actually kind of run. So the objectives I have when I read this is I wanted to design and construct a small-scale testing apparatus that mimics silt fence that are actually installed in the field. So silt fence in the field is usually at least 2 feet tall. I've seen some silt fences go up to 3 or 4 feet, which technically it's not really necessary to impound that much. It's kind of hard to, just from the hydrostatic forces of the water. So let's figure out how we can design something that we can impound water, let's say a minimum of 2 feet. The next thing, we need to develop a test methodology that incorporates regional specific design criteria and procedures that are repeatable. So for the ASTM, it's a set amount of water and a set amount of sediment, no matter where you are in the country. So let's develop a test methodology that can be designed, let's just say for your state, for example. So when I did this, I designed it for the state of Alabama. You could take the process and apply it to any state in the country. It's easily repeatable. You just have to do the calculations. So once I had the apparatus and the methodology, then I want to actually do some performance evaluations on different geotextiles that I had access to that were pretty common in the state of Alabama. And I've since found out that some of these geotextiles go into other states and some of them do not. And then I wanted to compare my results to what the ASTM results are for these different materials that are out there. Because ASTM, as most people know, this is kind of the gold standard, what a lot of people rely on for good information. So I wanted to see how accurate they were when you're actually testing this in a field-like condition. So I built a small scale test apparatus out of plywood. It was not huge, but I could achieve what I was trying to identify with this. So the way this little apparatus works, instead of dumping just 20 gallons of water into it, I could dump as much water as I wanted to, and I could control the flow rate. Now I'll explain how I did that. But essentially, this is a plywood box that we could install a geotextile in. The beginning of the box has a 3-to-1 slope. If you remember back to the ASTM, it was 8%. I cannot tell you where the 8% exactly came from, but I chose a 3-to-1 slope here because on your typical job site, slopes that you're going to have are probably going to be in the 3-to-1 range. So I wanted to have that coming into this test apparatus. Then I wanted to have an 8-foot section that was on a 1% slope. So this is like at the toe of like a fill section, for example. And then I wanted to have a minimum of 6 feet in front of the geotextile, and then I left 2 feet downstream of the geotextile so I could have room to do testing other things later on down the road, which I'll talk about at the very end. So this gives me some storage area in front of the silt fence so I can actually store the stormwater runoff and let it actually impound up. The overall test apparatus was 3 feet tall. A few years ago, I did some structural analysis on different support posts for silt fence. And in order to get a silt fence to actually hold back 3 feet of water, you got to have some really, really strong support posts that are spaced really closely together. And that's just mainly due to the hydrostatic pressure that's applied to the silt fence. So I knew that I would probably never go over 3 feet, and I never did in any of the testing. So that's why I chose 3 feet as opposed to 4 feet. And then the test apparatus was 4 feet wide. It's just the width of a piece of plywood. It gave me a nice representative section of geotextile that I could evaluate. So when you actually look at this from downstream looking upstream, the one thing I noticed right off the bat is plywood it's not a good container for water. Obviously, even if you try to seal up all the joints, it still leaks a little bit. So I learned that if you put some polypropylene in here and line the whole test apparatus, it works really good for helping seal everything up. And even for the geotextiles, when you put the polypropylene in there, we could take some construction adhesive and caulk up so the geotextile would actually seal to the polypropylene all the way around. So for every single piece of silt fence I installed, I used at least 2 caulk tubes of construction adhesive to help this stuff stick and actually help seal it up. That way I had no leaks around the outside. And then I put the 2x4s in there and put some screws through them, and that really held it in place. So this installation process worked really well for evaluating these different types of geotextiles. So for the water, we had a blue water trough, and the way I would control the flow rate here is we had a small pump that we would put in our supply pond, and it would pump water into the tank. And then I had these valves on the back, and because my flow rate was so low, I only had to operate one of the valves. But essentially I could operate this valve and control how much water I'm letting out, and I could actually maintain a water level within the tank. So as long as I had a constant head in the tank, the flow rate that was coming out of the front, I would be able to control that for all the tests. So we had this tube hooked to the side of the tank, and we made this custom it's essentially a V-notch weir flow rate measurement device. So we did some calculations based off a V-notch weir flow rates and figured out that the depth over the bottom of the V-notch could be correlated to a certain flow rate. For this particular test series, my flow rate was 0.04 cubic feet per second, and I'll explain how I got to that earlier. But as long as the water in the tube hovered around that 0.04, I knew that I was in pretty good shape. So on the front, we had a CNC machine cut us a V-notch weir, and we installed it and sealed it up on the front of the tank. So when we filled the tank up, the water would flow out of the V-notch weir, and it would hit my little splash pad. So the water would actually go into my apparatus, and then I had this little mixing trough area. So this is where we would actually introduce the sediment into the water so it can mix a little bit before it got all the way down to where the geotextile was at. So that's what these 2x4s that are nailed across the top of here are for. So this is just a little video of one of the undergrads I had helping me, but you can see we got water coming in. We knew we pre-filled buckets to a specific rate, and we knew we had to empty each bucket in a 2-minute time period. So we just slowly dumped the sediment in by hand over that 2 minutes. And we ended up getting a pretty good flow rate going down into the test apparatus. So you can see it's going down, it's mixing somewhat pretty well, but we got sediment laden water down at the bottom in the tank, and the tank's filling up like we anticipated. So this introduction process worked really, really well. And this over the ASTM allows us to run as long as we want to, as opposed to just having 20 gallons and opening the valve and letting it go in a very short amount of time. So this mimics more like what you would see during a rain event. The next thing that kind of gave me assurance that we were kind of doing this the right way is when you would let the water drain out of the tank, you could actually see the sediment deposition. So you would have your coarser material up on the 3-to-1 slope, which is pretty common when we see this out in the field. You'll see your coarser material fall out first. And as you progress toward the geotextile in this image, it would get finer and finer material until you are right there, right in front of the geotextile, where it's a very clayey, fine silt type material there. So it worked exactly how we thought it would when we designed it. So for the flow rates, so we came up with a theoretical flow rate based off a few different assumptions here. And again, this is for the state of Alabama, but you could do it for any state you wanted to. So the design storm, we chose a 2-year, 24-hour rain event. For Alabama, that state average is 4.43 inches, and it is a type 3 distribution. For the soil, for the hydrologic soil characteristics, we went with newly graded, so that gave us a curve number of 88.5. And then in Alabama, they have a standard that says when you are designing silt fence, that no more than a half an acre can drain to 100 linear feet. So that kind of gave us our drainage area that we were working with per linear foot of silt fence. So when we kind of take all this and put it into the model that we came up with, if we have a drainage area that's a half acre and we scale it down to the drainage area for a 4-foot section of silt fence, we get 0.02 acres. So the peak flow, we would plug into the hydrograph for this distribution area, and we had a peak flow rate of 0.06 cubic feet per second. If you do a 30-minute average for this, it would be 0.04 cubic feet. So that's where the 0.04 for our flow rate came from. When you take that into consideration, over a 30-minute test period, we end up with 72 cubic feet of water that we're going to introduce. Or if you convert that over to gallons, that's roughly 540 gallons almost. And based off the dimensions of the tank that we created, the test apparatus, we knew we could hold that much water in there. So we knew that this would work based off the design calculations we did. And again, you could use this same process and come up with a flow rate for any other state if you wanted to. For how much soil we needed to dump into the test apparatus. So we used the modified universal soil loss equation, and a predecessor of mine, Mr. Alan Bugg, had done an analysis on this. And he had determined that for Alabama, you needed 56 pounds of soil per linear foot of silt fence. And he had already done some large scale testing with this. So in order to stay consistent with this, I just wanted to scale this down from, he was doing a 20-foot section of fence. I was doing a 4-foot section of fence. So our introductory rates per linear foot stayed consistent. So that 56 pounds per linear foot times 4 feet, I need 224 pounds of soil. So when you break that down over a 30-minute test period, that's 7.5 pounds per minute. So when we filled up the buckets, we made sure we put 15 pounds of soil in each bucket. For the soil that we used soil that we had on site because it's Alabama native soil. If you look at the USDA classification, it is a sandy loam. We have the other classification for it too, but I just cannot remember what it is right offhand because it's a few years ago. But if we needed to bring soil from another state, we could absolutely do that. So some other projects that have taken place at Auburn, they've trucked soil all the way from Iowa down to Auburn to do different tests for different state DOTs based off the soil characteristics they have in their state. So bringing in soil from somewhere else and doing it is also completely possible. So what was the testing process like? So I wanted to make sure that I had enough samples that I could get some averages, and that way I could find if I did one experiment wrong or something didn't look right, I could catch it and kind of go back and analyze what had maybe happened. So for each geotextile that we selected to evaluate, we did 3 installations. So what I mean by installation, you get a new piece of geotextile, you install it, and then you run 3 simulated storm events back to back. So you install it, let's say on a Monday, you run a simulated storm event on Tuesday, you let it dewater, run another one on Wednesday, let it dewater, run another one on Thursday, let it dewater. That would be the end of the series. So you had 3 back-to-back storm events, so you could see how the actual performance changed over time. So you do that for the first installation, then we would take everything completely out of the test apparatus, and we'd completely start over again. We'd put a new liner in it, a new section of geotextile, do the whole process again. So essentially for one geotextile fabric that we were interested in evaluating, it would take us about 3 weeks to get all the data that we needed. And we did that for 5 different geotextiles. So when we're installing this, some key things that we did to gather data. So the first thing we did is we put a water level logger in. So because the geometry of this test apparatus doesn't change, and we knew what the incoming flow rate was, and it stayed consistent for every single test, we could use the water level logger to essentially electronically track the depth of the water in the tank over the 30-minute test period, and we could calculate how much volume of water we were retaining. So we knew how much water was coming in, we knew how much water we were retaining, so we could calculate how much water was actually passing through. And this is highlighting just the tank, and we knew the dimensions. And the silt fence were installed in the same exact spot for every single test. The next thing is we needed to gather some water samples. So we gathered water samples from several different locations. So the first location is we had a little submersible pump hooked to a hose pipe that we always sat in the bottom of the tank, and it always supplied us with a water sample from the bottom of the water column. So as the test progresses, the water level actually goes up and increases. So we always wanted to pull a sample off the bottom to see what that was like. The other sample we wanted to collect was on the surface of the water. So as the surface water goes up, we always stayed sampling off the top. And what we realized is that as the depth increases, the water quality on top improves when you compare it to the bottom. So if you can get 1.5 feet of water impoundment, you're doing really, really well at just improving water quality just by impounding it that way. So that's one of the unique things that we found by doing this. And then the last sample that we collected is we collected it downstream. So as the water passed through the geotextile fabric, we had a little sampler. We would go up and we'd take samples. And we had a sampling regime that we followed for every single test. And we had all these water samples, and I had a lot of undergrads running water samples to actually take a water sample and actually get a number out of it. So that's the different locations we collected water samples so we could see what was going on. For sediment retention, I told y'all that we weighed out the sediment, we weighed out the soil in buckets before we actually introduced it. So we knew how much soil we were putting into this apparatus. Because we had the plastic lining in there, we were able to remove all of the soil, even the muddy soil, and we laid it out on the asphalt on a piece of plastic and just let the Alabama summer sun bake it all day long, and it would drive off the moisture. When it got dry enough that we could actually handle and scrape it out of the buckets, we actually put it in a big metal wash tub. And because we're at the Center for Asphalt Technology, they got some giant ovens that they use for asphalt. So we'd take these giant tubs and go put them in the oven and dry them all the way to where they were completely bone dry. And then going back to the original soil we had, we knew that there was some moisture in that soil when we filled up the buckets. So we would take a little sample and we would dry it out to figure out what the water content is of the soil that we were putting in. That way we could back calculate what the dry unit weight was, or the dry weight total. And then we could take this again and figure out what the dry weight was at the end. So this is how we determined how much sediment had actually been retained. So this is one of those tubs. You can see it's dried up and it's pretty hard clay. And then we knew what the weight of the tubs were, so we could actually weigh this up and see how much soil we actually retained. So it's kind of a mass balance. So we knew took water content into to consideration. So we knew exactly how much soil we put in. We knew exactly how much soil we retained. So when we start comparing these two processes, the ASTM and this new innovative small scale testing. So when you start looking at the focus of these tests, so ASTM focuses on filtering efficiency and flow rate. For the one that I developed here, I was focused on sediment retention, flow rate, and water quality. What is happening to water as it's going through all these different processes? The design storm. To my knowledge, the ASTM does not have a design storm that it actually follows. But for us, we chose the 2-year 24-hour. We could change that if you wanted to go up or down from that. The drainage basing area, the ASTM doesn't have one that it specifies. For us, we knew we were looking at a drainage area of 0.02 acres. The flow rate for ASTM, when you actually do the calculations for it, is 0.177 feet cubed per second, and we were at 0.04. So their flow rate is higher than ours. But I want to point out that the test duration for the ASTM is 0.17 seconds. So it doesn't take very long to empty that 20-gallon tank, where we would run water for 30 minutes nonstop. And then the sediment loading for the ASTM, 0.33 pounds, and for ours, we were 224 pounds over that 30-minute period. So that's just a comparison between the two processes. So the 5 different geotextiles that I evaluated, these are all commonly used in Alabama. So we chose 2 non-woven. One was needle punch, one was spun bound, and then we chose 3 woven geotextiles. And all of these geotextiles that we selected are monofilament. And because each one of them had a different color, I just called them blue stripe, red stripe, and green stripe. It was pretty easy to kind of keep them separated, and you can kind of know which one goes where. So these are the 5 different ones we looked at. So just to kind of make sure we all on the same page, what slit film is and what monofilament is. So slit film is essentially you have a roll of some type of material, usually some type of plastic, and they take blades and they cut it into sections. And then they take another roll and they weave it together. And that's what creates a slit film geotextile. If you look down in the bottom left corner, you can see how it kind of looks when you have these put together. For most large construction projects, at least in the Southeast, these don't work that effectively. You may see them typically on like a residential lot type project, but if you're starting to get really big, like heavy civil projects, this material, based off what I've seen in the field, is not the best. If you get out of the Southeast where the rain events are not quite as intense, these could work pretty well, like out in the Midwest potentially. But for monofilament, essentially you still have the slit film type material, but it ends up having a weave to it. And this slit film is then filled in with extruded plastic strains. So there, instead of being a little film, it's actually a little tube, if you actually want to think of it that way. So this actually allows the geotextile to have a slightly larger pore opening. So that could be beneficial for us. Based off what I've seen in the field, these tend to also be a little bit stronger just from a tensile standpoint. Now, I haven't done any testing on them. This is just field observations. So everything we evaluated was monofilament. So I went online and I tried to find all the information I could, and I took samples of what I had to try to figure out all the different characteristics of it. So for all the different geotextiles, I tried to figure out what the weight was, so ounce per cubic yard of material. I tried to identify what the filament width was in the machine direction as well as the density, and I also tried to identify what the cross machine direction density was. We looked at the apparent opening size for all these different materials, as well as the published flow rates based off the ASTM test that had been done on them in the past that was available online. So this is just a summary of the properties of all the different geotextiles we looked at. So they all varied a little bit in some shape or form. So this is the actual testing. So what I have here is the two nonwovens, and this is a time-lapse video, and I tried to line the images up as closely as I could, as well as when the water starts flowing in. So when you actually look at this, they actually both fill up very similarly, and you can see me taking water samples as the water's coming through them. So this was a very unique process, and that we were able to kind of get these, and you can actually visually compare them and actually see, do they actually look like they're performing pretty similar from an impoundment standpoint, and just based off the angle of the camera that I tried to put in the exact same place every single time, it's a pretty good comparison. So I was very happy to see that these two materials perform pretty well from an impoundment standpoint. So moving on, looking at some more time lapse. So I wanted to compare the red stripe and the blue stripe. And again, these are lined up as closely as I could. And this is the flow coming in over the 30-minute test period. And you can see them starting to impound. One's kind of impounding a little bit more than the other one. But it's not a giant difference. So overall, this actually functioned the way that I thought it would as well. So it was pretty interesting to actually sit back and actually look at these and actually see kind of what's going on. The one thing that I noticed when I started watching these is how fast one dewaters over the other. And I wish I would have kept the cameras going longer, but I only kept them going 15 minutes. But some materials will dewater significantly faster from a mathematical standpoint than others. So I want to show one more comparison. So I compared the red stripe and the green stripe, and you can see that they both fill up very similarly as well. So they're filling up, water's passing through. They're all doing a pretty good job of actually retaining the water and actually letting the water that's on the surface pass through the geotextile openings. The one thing I want to point out about these videos is that the videos that I'm actually showing you right now are on the first simulated storm event. On the second and third, you may not see any water coming through these geotextiles at all until you're 10, 20, almost sometimes 25 minutes into the video, because the pore openings on the front of the geotextiles have just become clogged, and it's very common to see that. But just from a clean standpoint, no sediment whatsoever on the front of them. They all work pretty good. So one additional thing that I wanted to play around with when I was doing this, and I threw this in just so y'all could see it, is I was curious what sandbags would do. I know it's not a geotextile per se, but the geotextile the bag is made of is kind of interest. So we filled up some sandbags, installed them in here, tried to get them to lock together the best we could, and started running a test and collect data throughout the whole process. And I wasn't paying attention what was going on here because this was happening a lot slower than it actually is on the video, but you can tell that the sandbag started sliding back, and then I just had a complete blowout, and I thought that was a pretty cool video to show. But that's one thing I learned by doing this, is that when you have a material you're just setting in there, you got to have a means to hold it in place. And that would make sense out on the job site as well. I mean, you need some type of process to hold things still. So when I actually got to doing the calculations based on the water level logger data to figure out what the flow rates were, I was very interested in these results. So you can see the installations, you can see each type fabric, and I threw the sandbags in there too, as well as the average for all three tests. So you notice that the averages for each of the geotextiles that I evaluated, that flow rate is nowhere near what the published value is. So this was a very interest to me. I was like, so a lot of people are relying on this ASTM data to figure out what the flow rates are, but in reality, when you start having this geotextile installed in the field, you have multiple storm events, you have sediment-laden flow coming in, the flow rate that you're getting through these is nothing like what you would think it would be. I want to point out one number here. So if you look at the green stripe, you see the installation 1 and installation 3 are pretty close to each other. There's some variation, but that's a pretty normal variation. But installation 2 was extremely high. It's almost double the other two. So when I did this calculation and figured out this number, it threw up a red flag. It's like, something is not right here. Something went wrong. So I had to go back and I started going through all the pictures I took. So before every single test, I would take pictures. During the test, I would take pictures. When the test was over and the water drained away, I would take pictures. And I was like, there's something different about installation 2 compared to installation 1 and 3. So when I went back and started looking at pictures, this is what I found. So when I started looking at this, when you install this, you don't see it. But when you start looking at it closer, you start to see these little white dash lines almost in this one section of the geotextile. And when I saw this in the pictures, I was like, I need to look at this further to figure out what's going on. So I went back to the test facility and I had a roll of this material and I rolled the entire thing out on the ground. And there was just this one little section that we had cut a piece from where these little white slits were at. So I took a little ruler and took some pictures of this. So this is where the geotextile, it was woven together, and for some reason or another, it had shifted and these little white openings had opened up in this little section of fabric. And I made the assumption that this was probably manufactured perfectly right, and somewhere along the process of it getting packaged, shipped to us, when we got it, us handling it, unrolling it, rolling it, cutting sections off of it, that these little fibers had gotten moved around in this one little section. So I cut about 10 feet off of this roll and got rid of it. And when I did the third installation, I made sure that when I installed it, there was none of those little white slits in there. So there was just one piece that was bad from some reason or another. So we got rid of it and we installed a good one. And this is what gave us the good results on the third run. So that's what I investigated, what I found out, and the results I had for that. So the one thing I want to point out now, next, moving on, going back to those published flow rates, is that ASTM D4491 is what's typically used to evaluate the flow rate of geotextiles. So the way this thing works is it is a column of water that is placed on top of the geotextile. So the geotextile is actually installed about right in this area. And water is then passed through the geotextile vertically. So vertical flow and horizontal flow for like a silt fence that's standing up is very different. So that's one red flag for this particular test. When you're trying to evaluate it, how is it going to work as a silt fence when we're talking about geotextiles? The next thing that is interesting about this is that they use clear water. So there's no sediment of any kind in this water. So it's obvious that if you have a geotextile that's flat, you have a column of water pushing down on it, and it's all clean water with no particulates in it whatsoever, that you're probably going to have much higher flow rates than if you had the geotextile turned up on its side. So water's having to go sideways, and then you have all these soil particles in there as well. So while this is a method to evaluate geotextiles consistently, I don't think it's the best method to evaluate the flow rate of a geotextile when it's going to be installed as a silt fence. So the method I came up with gives you a little bit better representation of what to expect out in the field. So moving on to sediment retention. So I told y'all I knew how much sediment I put in. I knew how much sediment I took out because I dried it and weighed it. The sediment retention results were all really good. So for the nonwovens, I had a 97 and a 98% retention, which is what's to be expected for a material that has a very small pore size that holds back a lot of water. For the monofilament geotextiles, I ranged anywhere from 87 up to 94%. So again, it's still a good retention rate for all these geotextiles. So when you're actually thinking about, does this retain sediment? I'm not talking about filtering sediment. I'm talking about retaining it upstream. They all do a pretty good job. Even sandbags, before they blow out, do a pretty decent job of retaining sediment upstream. So again, based off dry weights. So the next thing that I had to come up with is a way to evaluate the water quality that is unique, that can tell me some good information. So if you look at the cross-sectional view of the test apparatus, and we have the geotextile installed in the pump, and we know the different locations where we took. So we took water off the surface, we took water from the pump, and we took water downstream of the geotextile. So I have 3 different locations that I can compare water quality to. So the first thing that I wanted to do is I kind of turned the coin. What is the sedimentation efficiency for the geotextile? So if I compare the water quality at the bottom of the impoundment and compare that to the water quality at the top in the impoundment, I can figure out, is this setup, is this geotextile facilitating the sedimentation of particles or not? And if it is, how well is it doing it? So you come up with a little sedimentation efficiency equation where essentially you say that sedimentation efficiency is going to be what the water quality is on top compared to what the water quality is on the bottom. So most people would think, well, the water quality on the top and water quality on the bottom of a small impoundment like this, especially if it doesn't get over 1 foot, it's not going to be that big of a difference. But we found that it can be a pretty significant difference. So this was one methodology for evaluating water quality improvements, sedimentation efficiency. The second one was filtering efficiency. So filtering efficiency is like what you'd think. As the water passes through the geotextile, is the geotextile retaining any of the soil particles? And if it is, how much? So we have a filtration efficiency where we're looking at the downstream water sample and we're comparing it to the upstream water sample that's on the surface. And I have had people in the past ask me, Why did you choose the surface of the impoundment as opposed to where the pump is at, so the bottom of the impoundment? So the reason I did this is because usually the flow that is passing through the geotextile is on the surface of the impoundment, because over time, the geotextile that's submerged, it becomes clogged with soil particles. So really the only water that's passing through the geotextile is the water that's closer to the surface of the impoundment. So I felt like that was the most appropriate way to evaluate this, because we have clean water, or excuse me, we have cleaner water on the surface than we do on the bottom. We know that for a fact. So let's compare the surface water quality to that of downstream of the geotextile. So when I took these, and I took them for all of the evaluations that we did, I took averages of all this, and then I plotted it on what I call the sedimentation efficiency plot. So let me explain how this thing's set up a little bit. So if you look on the left, you can see I have 0% all the way up to 100%, all the way down to a negative 100%. So anything that's negative in the red, water quality went down as opposed to improving. If it's between 0 and 100% positive, that means water quality did improve, so that would be in the green. Then along the x-axis, I have time. So I ran the test for 30 minutes. So that's the test period. And then I would continue to gather water samples for an additional hour and a half. So that's during the dewatering period. So that way I could see what it's like during the test. So this is when it's raining on your job site and water's actually running to the silt fence. And then after the rain stops and you actually have a dewatering time on your job site. So that's what I'm looking at. And I'm comparing the surface water to the bottom of the impoundment. And then I tried to color code the lines to the geotextiles. So you can see during the 30-minute test period, sedimentation efficiency is pretty good from all of the materials. So it's creating an impoundment, allowing the soil particles to fall out of suspension. Then when you get into the dewatering period, so this is looking at what is the sedimentation occurring upstream of the geotextile when there's no water actually running into it. So you actually have a still impoundment. So there's no turbidity. Well, there's turbidity. There's no turbulence, excuse me. So we look at this and you can see that the green stripe did very, very well during this dewatering period. The red stripe and blue stripe, not as much. Those were the monofilaments. And then you can also see that the non-wovens, they were hovering around the 0% mark. So nothing notable there either. But the main thing is sedimentation efficiency was really good for all of them during the simulated rain event. So that's what we were really looking for. So when you look at this filtration efficiency, so how well is the geotextile filtering these soil particles out as the water actually passes through the geotextile? So during the test period, none of them really provide any enhancements. So technically, based off this data, the water quality on the surface of the impoundment is better than the water quality downstream of the geotextile. So that was kind of interesting. But that's just when the water is actually coming into the testing apparatus. Once you get into the dewatering phase, this is when the flow rate really slows down because you start to have a lot of soil start to accumulate on the face of the geotextile. So you can actually start to see, you can see that the dotted line, the non-woven spunbound, had a pretty good improvement in water quality during this dewatering phase. So did the red stripe. So some things to note here is that while you see an improvement in water quality just for about everything right here, the flow rate during this dewatering period was dramatically different for all of these, really depending on how much soil particle actually accumulated on the face of the geotextile during that testing process. But from a water quality standpoint, all did pretty well. So some conclusions that I want to wrap up here, because we are getting close. We've got a little bit of time left. So, effluent flow rates observed during the testing for non-woven geotextiles were 43% lower than woven geotextiles, just overall, looking at everything as a whole. The published effluent flow rates do not accurately characterize infill flow rates under sediment-laden flow conditions. They may be helpful to do comparisons if you're trying to determine what material you may want, but those numbers cannot be relied on to be really realistic when you actually use them. The average sediment retention for non-wovens was 97%, for the wovens was 91%. Anything over 90% is pretty good from a sediment retention standpoint, so both did very well there. And the average sedimentation efficiency was 46% during the testing period. So this is when water's coming in. So this is really, really impactful here. And then the average filtration efficiency was 19% during dewatering. So all that was all useful information. So that was how the test apparatus was developed, what it's based off of, and some of the results we got from this series of tests. So the next thing I want to point out before we finish up here is that the question is often asked, are double row sediment barriers effective? And I was like, I don't know. I've never really evaluated that before. So I actually used this same methodology, and I did a whole nother series of tests where I looked at putting in a G2 double row silt fence into the small scale test apparatus, and I evaluated them to see, does 2 silt fence installed in series provide enhanced water quality? When I had that data, I went on and said, well, instead of putting 2 geotextile silt fences up, could I potentially put a geotextile and something else up? Some other type of sediment barrier test apparatus, not test, sediment barrier into the test apparatus. And see, can I get water quality improvements from something else? So I did this for, I think, 5 or 6 alternatives to a double row silt fence, and I got some extremely interesting data from this. I don't have enough time to share it all here, but I'll probably do another webinar. If I had to guess, I'll probably do another one this summer, and I would like to share that with y'all if y'all are interested in that, to see what does a double row silt fence do using this same methodology, and are there ways to improve it using alternatives to a second silt fence? So with that, that wraps up what I wanted to present today. This paper on this particular information I presented today is published and it is free. So if you scan this QR code, it will take you to where that paper is at. You can download a PDF and you can actually read all this information for sure. It is very useful if you're trying to just get an enhanced understanding of what's going on. If you have questions about silt fence geotextiles, you can see my email right there on the bottom of the screen. I'm happy to try to provide any answers that I can. But with that, I thank y'all for logging on and listening to me ramble on for roughly, 50 minutes? All right, thank y'all. I'll turn it over to Mike.
Blake, thanks for sharing your research with us. This is really cool stuff. I've seen this presentation a couple times. I always learn something new. I guess as we wait for questions to come in, I wanted to start out by asking, is there a clear-cut difference between one type of geotextile versus another? Is there one that we should be using? Is there one we should be avoiding? They all seem to have really high sediment capture rate. Does it make sense to pay twice as much for a fancier geotextile than just a simpler weave pattern?
Mike, if there's questions, I can't see them.
Yeah. Were you able to hear my question, Blake?
I'm trying to get I hear you talking, but I don't know what you're saying.
So
the microphone's working. I'm trying to get the speakers working.
I gotcha.
Give me a second. All right, go.
All right, so can you hear me now?
Nope. Try it again.
About now.
Yes.
Okay. So big picture takeaway, is there one geotextile that's better than the other? Should we be investing in one versus another type? Should we just go for the cheapest one? They all seem to have a high sediment capture rate. Um, is it a filtering thing? Is this an impoundment thing? Just kind of summarize it all there for us.
So just as a overall evaluation of the types of geotextiles, based off what I've seen in field and through testing, a monofilament geotextile tends to be like the best like product you can get. That's not one particular brand over another, but it tends to have a very good sediment retention. But because of the way it's manufactured, it allows flow to actually escape. So the dewatering, when you use a non-woven, yeah, they have a higher sediment retention, but they blind up so fast that after a few rain events, it's not going to dewater at all. So you're essentially just you could put up a piece of solid plastic and you would have the same scenario. So that's the big thing. And then the next thing for the geotextile itself, like if you're trying to impound, let's say 1.5 feet, 2 feet of water, you got to have supports that can support that without having silt fence sag between the supports. So usually you need to put supports closer together, maybe even stronger supports where you have maybe an area of concentrated impoundment. So I know most people try to install geotextiles that are silt fences on the contour. In the real life, it's really hard to achieve that, but you kind of know where all the water is going to run to. So if you kind of beef up the structure in that location, so the silt fence can actually hold up, or you can even put an innovative dewatering device. We've had one we've developed and tested. There's other ones out there that you can use and put in there. It really helps. And I think it really works pretty well.
I have a question that came in from John Isley. So based on your findings, if you had a steeper slope, let's say something greater than 3-to-1, do you think woven or non-woven would be best for those situations?
As long as, so this is, I haven't tested this, but as long as you give room for the impoundment at the bottom of the slope, so you could have a 2-to-1 slope, for example. So that's pretty steep. As long as you go a few feet, I'm gonna say at least 4 feet, 6 would be better, from the toe into a kind of a more flat area. I'm not saying it has to be perfectly flat. It'll probably still work pretty well. But it also it's also a function of how long is the slope. So like in Tennessee, when they do road construction, you may have a 2-to-1 slope that's 300 feet long in some areas because they have to cut that much out. And it may be half rock, half soil. So it may be areas that are completely impervious that you'll have a lot of runoff on. So it all depends on where you're at and the type of flow rate you're anticipating.
Blake, if you could summarize your key takeaways from a designer standpoint, what would you want them to take away for a designer who's spec in or placing silt fence?
Again, it depends on the situation. If I was a designer, I know that non-wovens, as I said, you're not going to get any flow through that. So I'd stick with the monofilament. If I was a designer, I would definitely not spec out the slit film where you have the two slits come together. That just completely take that off the table. I wouldn't use that at all. And it depends on if you're a designer. It depends on what your state uses or allows. So some states allow you to use like hardwood post, which hardwood posts are extremely strong. Like when I did when I did a 3-point bending test on hardwood post, they are super strong. They're hard to get in the ground sometimes. Steel post, most people sell the lighter weight steel post, the 0.95 pound per foot. They bend too easily. You need to have at least the 1.25, which is what is called out by AASHTO, if I'm not mistaken. But they also make a 1.33 pound per foot post. And I tested those as well. And I'm not saying you have to use those on the whole fence. You just need to use it where you're going to have that area concentrated impoundment. So where is the water going to run to? Put it there. So that's from a design standpoint, those are things that I would focus on. That may have answered the question or it may not have.
Blake, have you compared these results to other types of sediment barriers like hay bales, mulch logs, other types of sediment barrier methods?
This is maybe. The answer is maybe. So I haven't installed just these different sediment barriers and tested them by themselves. So for example, a straw wattle to see how it compares. So I'll go ahead and give a little hint that some of the alternatives I used as opposed to 2 silt fences, I had 1 silt fence and then a straw wattle. And I had other different types of wattles as well. And these combinations work really well. So if I had to make a recommendation, if you're going to do a double row anything, do a silt fence first, monofilament, and then do a second row of something else, something that's maybe tubular. So it could be straw, it could be Excelsior. There's one that works really, really well, but I don't know if it's available all over the place. But I don't want to give it all away. I want to be able to come talk to y'all again.
So that's your follow-up research project you're talking about. We'll do another
Yeah.
webinar on. Gotcha.
Yeah.
Very cool. Blake, there's a lot of boutique type of silt fences that are marketed out there that have all these special properties. Is there a place for them? Have you tested those? How would you expect those to perform based on what you've seen so far?
Based off the few things that I've looked at that are considered specialty, unique, I don't know the pricing on them because I haven't searched it that hard. But for what I would assume, based off what I know, you could go with something that's more generic and probably get the same or very similar results by implementing maybe some unique practices for the installation process or how you actually choose where you place the silt fence. So it could be advantageous depending on the circumstances, but generally speaking, something that's pretty generic, kind of common would probably give you very similar results. Maybe not exact, but then there could be certain situations where that unique design property that this particular product offers would work really, really well in this application.
Yeah, every time we do a project like this, I see that it comes down to a function of how much you can impound and how much you can slow down the water.
Yeah.
It seems like as long as you're able to impound and slow it down, you're going to get some sediment capture benefits.
Say that one more time.
It seems like, the more you impound, the more you slow down the water, the more benefits you'll get.
So if you can slow down the water, that's the key thing. Because like I said, if you go back and look at those charts, which I could pull them back up, the sedimentation efficiency is like where you're getting all of that sediment retention. The filtering efficiency is there, but compared to the sedimentation efficiency from a statistical standpoint, it's negligible because it's just not that big of a change. We're about out of time.
Yep, we can wrap it up. Thank you, Blake, again for presenting. This webinar is being recorded, so we're going to post it on our YouTube, and anybody else can watch it later on. You also get a follow-up email. I think tomorrow it'll go out. That'll have a link to being able to download PDH for it. It's a 1-hour PDH. If you have any issues downloading it, please let me know. I know the system's a little clunky. That's what we have to use here. But otherwise, Blake, thank you so much. And we look forward to having you again on our TigerStream webinar. And stay tuned for an email for next month's webinar. We haven't set a date yet, but we'll send out something pretty neat. So, all right. Thank you, Blake. Thank you all for joining.
Yep. Thank you. See y'all at ICA if you're coming.